Hello world, time for another homebrew Z80 video. This one might be a little bit of a boring one for some of you. I'm not going to show you, like you might think looking at the screen right now, an exciting new expansion board for the LM-512. I'm actually going to tell you about an expansion board that I haven't been able to get working. So one of the reasons that I went such a ridiculously long time between video updates recently is that I had a number of projects for this computer that I had started working on, but just, couldn't get working to the point that I wanted to record a demonstration video. So, since I'm trying to do a bit of a catch-up video burst now, I thought rather than making you guys wait any longer, I would just show you things as they are now. So, what you can see right now is a failed UART expansion card. So the LM-512 has two UART channels built on to the board, but they're both in use pretty much all the time. One of them is used for the I/O terminal, and obviously you can't use that for anything else, or else you can't actually interact with the machine. And the second one I have hooked up also to my development Linux machine, and I use that to transfer Z80 machine code that I cross-compile on my Linux machine into the LM512's memory. And that being able to transfer programs over that serial cable is tremendously useful, compared to having to copy them either onto the CF card or to burn an EEPROM. It's sped up my development process so much, and it's so handy that I am in no rush to lose that capability. So I basically have 0 free UART ports, which is kind of a pain because there are a lot of interesting things I'd like to do with the computer that require extra serial channels. So one of those would be a MIDI card. So I have all the stuff for this. I have here the DIN5 connectors that MIDI cables use, and the octo isolator and all that. You could easily build a little MIDI card, and that would let me either write a MIDI sequencer program for the Z80 and sequence external hardware synthesizers, or I could use the AY38912 expansion sound card that I showed in my previous video. You could control that with a MIDI keyboard or a MIDI sequencer running on a PC or something. So that'd be something fun to play with, but it needs an extra UART channel, and it needs a 5-volt UART channel, not the plus or minus 12-volt RS232 channels that I have on the main board. The other thing that obviously would be really cool is using a UART channel to connect the LM512 to a microcontroller, to an AVR or a PIC. There's a ton of stuff you could do with this. All of the peripherals on modern microcontrollers, which aren't available natively on the Z80. An I2C bus, an SPI bus, analog digital converters, comparators, all that kind of stuff could become accessible over a serial bus. Over a serial connection powered by UART. Microchip make these fantastic, I should have looked up the serial number before I started recording, but they're Ethernet controller chips, and they come remarkably in a through-hole DIP package, which is super convenient for hobbyists. It'd be fantastic to build like a UART to Ethernet converter for the LM512 and be able to get it on the internet without having to use a Linux machine as an intermediary running SLIP or something like that. So there's a ton of stuff I'd love to do with UARTs, and so it'd be nice to have a lot of extra channels. And this board was supposed to give me 4 of them. So there are 2 chips on here, 1, 2. They're PLCC package chips. This is actually a surface mount package. It's designed to be soldered directly onto the board by industrial soldering robots, but it's kind of a hobbyist-friendly surface mount package because you can get through-hole sockets. So this is an example of one. It's for a larger package size than these ones, but it's got these connectors on the side which connect to the sort of, not a gull wing, but they're kind of these curved legs on the side of these packages, but on the underside it's just standard pitch through hole, so it'll work on a breadboard or proto board or what have you. So it's accessible surface mount, and you know, it's getting harder and harder to find things like parallel bus UARTs and stuff in the DIP package, because it's such obsolete technology. And sometimes, you know, this is not just UARTs, but SRAM, EEPROMs, all that kind of stuff. Sometimes you have better luck with the PLCC package. And so, you know, this being able to convert this is quite handy. Anyway, these are NXP chips. They are SC16C2552 BIA14s, I think. You know, semiconductor manufacturers can fabricate these amazing tiny silicon miracles, but they can't print clear numbers on black plastic to save their lives. It's really hard to read the numbers once the chips have been out of the packet for a couple of weeks. But yeah, SC16C2552 I think is the main part of the name, and each of these has 2 UARTs on it, and they're basically just the standard 16550 or whatever they are UARTs. There's one pin which controls whether you're talking to channel A or channel B, and aside from that, you know, it's a totally standard pin out, and you get all the normal UART inputs and outputs. And so these 4 odd-looking things here are, you know, they're just actually normal IDC connectors, 6 pins. So, you know, they're kind of like this thing here, which is a little bit more familiar looking, you know, for hooking in a ribbon cable. They've just got these, you know, mighty clamps on the side to kind of hold the connector in place. Kind of overkill for this project, but for whatever reason, these are actually cheaper for me to buy from my local supplier than the non-clamped versions. So, you know, these are just 4 beefy connectors, 2 per dual UART chip. There are 6 pins on there, so you can break out a receive line and a transmit line, plus 5 volts ground. I was going to carry out the reset line from the Z80, and then there's a 6 pin. I didn't know what I was going to do with that, but you know, you can't get these in 5 pins, so maybe sending the Z80 clock out on the 6 pin would be a handy thing to do. But at any rate, the idea is each one of these is a straight up sort of 5 volt UART channel, you know, with the power on it, so you could have a little microcontroller board hooked up to this. You could power it from this. You could talk to it over serial. You can reset it. You know, everything's there. Really nifty. You know, I built this up, and it did not work. It did not work whatsoever. It was really frustrating. I spent a long time sort of debugging it, you know, checking meticulously all these pins that nothing was shorted. You know, I was putting multiple oscilloscope probes on here to check the timing in case there was some sort of weird timing bug, and it didn't work, and it drove me nuts, and I ended up putting it away and not touching it for you know, for a month. And then one day, for whatever reason, I was rereading the data sheet for these chips, and I noticed something. I noticed that the reset lines on these UART chips is active high. You put 5 volts on there, you pulse it high to reset, and that's kind of backward. I think it's actually not that uncommon with UARTs, but in general, no, that's backward. The Z80 CPU has an active low reset line. You know, the real-time clock chip on my Z80 has an active low reset line. AVR microcontrollers are active low. Most things are active low. And so I didn't even think about that. I hooked the reset straight up to the Z80 reset line without even thinking about it. And what that means is that while the Z80 was running along doing its thing, and I was trying to talk to these chips and get them to do anything at all, the damn things were held in reset, so of course they weren't working. Luckily, you know, I've got some glue logic here for the address decoding and to choose which UART you want and that kind of stuff. And one of these is a 7404 hex inverter, and I had a couple of spare NOT gates on there, so I inverted the reset line and hooked it up again, and I thought, fantastic, this is going to just work, because I know when it didn't work in the first place, I tested everything so thoroughly, you know, I could find nothing else wrong. I thought it must just be the reset, or fix that and it'll work. I fixed that, and it kind of worked. This chip seemed to be working just fine. This one was acting really weird. And so I thought, okay, maybe while I was trying to debug this, I shorted something out with a probe and this chip's dead. Popped the chips out of their sockets, swapped them around, exactly the same thing. So both the chips are happy, it's something to do with this particular location on the board. You know, so I double checked all the wiring again carefully, no problems. You know, I've added these ridiculously oversized power supply bypass caps, you know, no difference. I did everything I could to minimize the differences between these two positions. So this guy's chip select is coming out of a NOT gate or something, and this guy's is coming directly from a source, and so there's a very slight difference of one gate propagation delay in the strobe timing for these two chips. And I thought, right, I'll get rid of that by running the chip select through a, you know, an OR with a 0 input or something to make the timing exact. And I did that. No difference, you know, as far as I can tell. Because, you know, all the data bus, address bus, everything is just wired, you know, daisy chained on these from the LM-512 expansion to this chip. You know, if there was a short on here somewhere, you'd have the exact same short on here. But, you know, this one was working fine, so I was utterly baffled. And, you know, I did a bit more playing around with it. What I was doing to test these real quickly is these chips have a scratch pad register in there at address 7, I think, and that's just a 1 byte storage thing that is on there as a convenience, I guess, for the programmer, and you can write a byte there and read it back, and it's just a scratch pad where you can store anything. And I was writing values to the scratch pad here and reading them back, and you know, I was getting the same value, it was working. I was writing them here and reading them back, and I was just getting 0 bytes always, you know, I couldn't store anything here. So I thought, this is working just fine, this is totally dead. With the more thorough test, that's not quite true. This one is working well enough that I can change the configuration registers and put it into a loopback mode, where it's sort of, instead of inputting and outputting on the serial pins, it just kind of, you write to the serial out, read from the serial in, and it sort of internally connects them, and so you can write in a byte and read it out. And I tried doing that, and it kind of works. Most of the time you write in a byte, you read it out, you get the same byte back. Sometimes you write it in, you write it out, and you get a different byte back. And so I probed around a lot of values, I took notes, you know, I figured out the binary expansions of the bytes I was sending, and it turns out that the highest and second highest order bits that you read out of this sometimes get scrambled. They never get scrambled when reading from the clock, from the scratch pad register, so it's not like there's a physical short on the lines or anything. It's only sometimes, and it's really weird. And at the end of the day, what I'm chalking this up to is just, you know, the realities of the way it's wired up. You know, this, you know, the LM-512's done like this, all my expansion cards are done like this. I haven't really had any problems, even though this is, you know, ugly and messy, and, you know, not all bits on the data bus have equal length, you know, cables, and, you know, there's all sorts of parasitic capacitance and really non-ideal stuff happening here. It's always worked for me, but I have to assume that this time it's caught up with me, and there's some sort of some kind of weird magic happening here, you know, crosstalk or something, you know, some kind of you know, abnormality coming from all this sort of electrolytic stuff we tend to ignore when we think of this as kind of a, you know, simple point-to-point connection thing. You know, there's a lot of parallel lines here running really close together. Something screwy is happening, I guess, and you know, the idea of reworking this board is utterly unappealing. So I think I'm going to cut my losses. I've wasted a lot of hours on this. Maybe one day I will have you know, a proper PCB fabricated with this design. That'll be a hell of a lot, you know, neater than this, and maybe it'll work. Maybe it won't. You know, if you have any other ideas for why this is acting in this weird way, feel free to leave a comment. But yeah, for now I'm gonna you know, I'm gonna admit defeat on this and stop wasting my time. Sucks not to have my UART channels, because there's a lot of cool things I can't do without them, but you know, sometimes I guess things don't work out. So there's one, not for the scrap heap, I guess, I'll throw it out, but I'll put it aside. Yeah, so that's one of 2 failed expansion cards, but you know, my next video I'll actually make sure I have something working to show you guys, so it's a bit more interesting. But yeah, other than that, thanks for watching, and I hope I can post another one of these videos sometime soon. Bye.